Larutan penyangga adalah larutan yang pH konstan meskipun diencerkan, ditambah asam atau ditambah basa. pH larutan penyangga tidak berubah sebab H+ atau OH- yang datang segera ditangkap oleh partikel-partikel zat terlarut. Ada dua jenis larutan penyangga, yaitu campuran asam lemah dengan garamnya disebut penyangga asam, dan campuran basa lemah dan garamnya disebut penyangga basa.
As hydronium ions are added to the buffer, the equilibrium shifts left according to Le Chatelier's principle. Initially, in this acetic acid acetate buffer, there is a new acetic acid molecule formed for nearly every hydronium added to the solution. As the added hydronium ions react with acetate ions, equilibrium between acetic acid and acetate ions is re-established. Only a very small amount of acetic acid ionizes to form acetate ions and new hydronium ions. The animation illustrates this process. Here, a hydrogen chloride molecule ionizes in water. The resulting hydronium ion reacts with an acetate ion forming acetic acid. Due to the small Ka of acetic acid, very few acetic acid molecules ionize to form acetate and hydronium ions.
Rewrite the equation again. So HA is in equilibrium. Everything's in an aqueous solution with hydrogen and its conjugate base. We know that there's an equilibrium constant for this. We've done many videos on that. The equilibrium constant here is equal to the concentration of our hydrogen proton times the concentration of our conjugate base. When I say concentration, I'm talking molarity, moles per liter, divided by the concentration of our weak acid. Now, let's take the log, or let's take the negative log of both sides of this equation. Actually, let me do something. Let's solve for hydrogen concentration. And what I want to do is I want to figure out a formula, and we'll call it the Henderson-Hasselbalch formula, which a lot of books want you to memorize, which I don't think you should. I think you should always just be able to go from this kind of basic assumption and get to it. But let's solve for the hydrogen so we can figure out a relationship between pH and all the other stuff that's in this formula. So, if we want to solve for hydrogen, we can multiply both sides by the reciprocal of this right here, and you get hydrogen concentration, and I'm flipping, well, let me just do Ka times, I'm multiplying both sides times the reciprocal of that, so times the concentration of our weak acid divided by the concentration of our weak base is equal to our concentration of our hydrogen. Fair enough. Now, let's take the negative log of both sides. So, the negative log, let me do that, negative log of all of that stuff, of your acidic equilibrium constant times, make sure, let me see, what green was I using, times HA, our weak acid, divided by our weak base, is equal to the negative log of our hydrogen concentration, which is just our pH, right? Negative log of hydrogen concentration that's the definition of pH. And I'll write the P and the H in different colors. So you know that P just means negative log, minus log. That's all at base 10. Let's see if we can simplify this anymore. So our logarithmic properties, we know that when you take the log of something and you multiply it, that's the same thing as taking the log of this plus the log of that. So this can be simplified to minus log of our Ka minus the log of our weak acid concentration divided by its conjugate base concentration is equal to the pH. Now this is just the pKa of our weak acid, which is just the negative log of its equilibrium constant. So this is just the pKa. And the minus log of HA over A, what we can do is we could make this a plus and just take this to the minus 1 power, right? That's just another logarithm property, and you can review the logarithm videos if that confused you. And this to the minus 1 power just means invert this. So we could say plus the logarithm of our conjugate base concentration divided by the weak acid concentration is equal to the pH. And this right here, this is called the Henderson-Hasselbalch equation. Henderson-Hasselbalch. And I really encourage you not to memorize it. Because if you do attempt to memorize it, within a few hours, you're going to forget whether this was a plus over here. You're going to forget this, and you're going to forget whether you put the A minus or the HA on the numerator or the denominator. And if you forget that, it's fatal. The better thing is to just start from your base assumptions. And if you weren't, and trust me, it took me a couple minutes to do it, but if you just do it really fast on paper and you don't have to talk it through the way I did, it'll take you no time at all to come to this equation. It's much better than memorizing it, and you won't forget it when you're 30 years old. But what's useful about this? Well, it immediately relates pH to our pKa, and this is a constant, right, for an equilibrium, plus the log of the ratios between the acid and the conjugate base. So, the more conjugate base I have and the less acid I have, the more my pH is going to increase, right? If this goes up and this is going down, my pH is going to increase, which makes sense because I have more base in the solution. And if I have the inverse of that, my pH is going to decrease.
Show how a buffer system is made and how it operates. Here we have an acetic acid solution. To the acetic acid solution, we've added sodium acetate, the salt of acetic acid. When you have the weak acid and the salt of that weak acid, you've prepared a buffered solution. Here we have distilled water, which will serve as our control in this demonstration. We're going to add some universal indicator. We now will add a base solution. First to our distilled water, then to our buffer, and then to our acetic acid. We notice that the buffer has changed in accordance with the color chart of the universal indicator to a basic solution. Let's add another drop to each of our solutions, and another drop. Our control no longer changes, and so now we'll focus on the buffer, adding 1, 2, 3, 4, 5 drops, and to the acid, 1, 2, 3, 4, 5 drops. Repeating the procedure. Beginning to notice a change in the acid that is not occurring in the buffer. Our acid is now changing from the acid range, moving toward the neutral. Into the orange. 5 more drops. We notice that the acid solution has already changed to the violet basic color. The buffer continues to be toward the neutral range. Let's add some additional base to just our buffer. Now we notice the buffer is moving into the green area toward the neutral. And finally into the basic. It requires a great deal more base to change a buffered solution than it did an acidic solution. Buffered solutions resist changes in pH.
Hey Dad, what are you doing?
What? I'm making a buffer.
How much are you making?
400 ml.
But you already have 500 ml water in your beaker.
So?
Don't you remember that solid also had volume? If you put that in, it's actually going to be volume effect.
Oh yeah, that's right. Let's rewind. What's up? It's me again, Dan. Today I'm going to show you how to make a buffer and pH it. I already weighed out the ingredients. Just gonna pour everything into a beaker. After we added in the ingredients, we're adding water. We'll be making a 500 ml buffer, so we're adding to approximately 300 or maybe 350. And then we'll let it stir till everything is dissolved. Okay, right now we're going to pH the buffer. The reading right now is about 10.69. We're going to pH it down to 8.8 using concentrated hydrochloric acid. What we're going to do is we're going to slowly add the acid to the buffer. The reading is going to change really fast right now because the pH is not in the buffering range of the buffer. But once the pH hits the buffering range, it's going to slow down. So right now it's at about 10.2. We'll keep on adding drop by drop. So the pH is now at 8.8. So right now we'll top out the buffer to 500 ml. So we'll be using a graduated cylinder. So we'll pour in the buffer slowly. So we have about 360 ml of buffer, and then we're just pouring water slowly till it reaches 500. And that's how you make a buffer.